welcome back. We're going to look at Chapter 10. This is Week 10 in CIT 15, and we're going to look at software programming. I haven't been through this PowerPoint presentation, so we'll be exploring it together, just making sure I'm recording here. Describe the importance of programming to both software developers and users. Let's talk about that. Like, why would programming be important to software developers? Well, it's their job. And then they get to build and create stuff. They get to tell machines what to do. But the most amazing thing about being a software developer is bringing something, giving birth to something, and bringing it to the world, something which is useful and which could help people. It's an incredible feeling, at least for me, to create something which then is useful to other people. And that you made it. You had the idea for it, and you created it, and then people enjoyed it, and it's an amazing thing to build something and bring it into the world. So and then users, like, software is amazing. Like, software allows us to more quickly do things, and so when you create software, what you really want to think about is, how can I extend the capabilities of humans? How can I make humans more efficient and more optimal? And so this is a good way to think about all inventions. And like with, humans, we like to go from one place to another. Well, originally all we could do was walk. And then maybe we harnessed the power of animals and we rode animals. And then maybe the bicycle and the train, right? And then maybe the car and the airplane eventually, and then rockets, right? Like, wow, now we're really getting places quickly. And then how do we optimize those things? Now we have Teslas and electric cars with better acceleration and, artificial intelligence that they could almost drive themselves now and can fairly well drive themselves. And so that, is like, how do we extend the capabilities of the human for transport, getting from one place to another? It's pretty extraordinary and amazing to see how we've done that. Likewise with communication. Originally there were no phones. We communicated. We had telegrams and telegraph wire, and so you could send somebody a telegram. And then phones came along, and wow, amazing. But if you called somebody and they weren't home, the phone just rang lonely. And then we got answering machines. Wow, we could leave a message, and then we could know somebody called, and we could call them back. And then, we got texting. Ooh, wow. Now we could just text. We don't have to call them. We could send a short message, right, via text. And so, right, for users, software allows us to extend our capabilities as humans and to be more efficient and to do things more optimally, whether it's moving from one place to another or communicating. And so it's really useful to think about how, whatever we create, how does it allow us to do what we like to do as humans? Social media allows us to connect with our friends and stay in touch with our friends more easily. So that's an example of that. Summarize the stages of the system development life cycle. So the system development life cycle, the SDLC, is just a problem-solving process. And you use so academics can be stupid at times. And instead of describing this as a problem-solving process, which we use all the time, they give it a name, systems development life cycle. And some people even talk about the programming development life cycle. And then in other fields, you might have other names for a problem-solving process, the scientific method, if you take science, right? But really, basically, the problem-solving process is like recognizing that something could be done better, either because of suffering, like, oh, I'm standing in this line in the hot sun, this sucks, there should be a better way to do this, right? Or just because it's working fine, but you see a better way that it could even be done. Like, hey, my driving car, how cool, but wouldn't it be even cooler if we could just teleport, like in that Star Trek TV show movie thing? And so, the first stage is just recognizing there could be some improvement. The second stage is to kind of come up with the idea of what that improvement might look like, and then do a little testing, like talk to users, beta test, create a prototype, see what people think of it. And then the next stage would be to like roll it out, right? Like, or to build it at scale, like, okay, let's make it larger and perfect it, and then let's roll it out, and then it's going to have a life cycle where it will then eventually die, and then we'll go through that process again. So that's kind of like the systems development life cycle. We We realize we need a system. We create that new system. We use that system. That system becomes antiquated. We throw it away. We get a new system. We go through that life cycle again. So that's the SDLC. But it's really a problem-solving process, right? Like, you solve problems all day long. Like, you're like, okay, you wake up in the morning, you're like, there's a little bit of a pain in my belly. Did I get punched? No. Right? You look for what the cause is. Maybe I'm hungry. You go in the kitchen, get something to eat. You eat, and then you look. Did that fix the problem? Yeah, that fixed the problem. So you identify the problem. You investigate the problem. You come up with a potential solution. You implement the solution. You evaluate the solution. Right? And is it working well? Great. And then, as needed, you repeat. So that's the problem-solving process. Define programming and list the steps in the program. See, there's the program development lifecycle. It's just another problem-solving process, right? It's slightly different. And programming is giving instructions to a computer. And you're learning how to do that in our little exercises. So you're just telling the computer, look, I want you to do these things. And it can seem really rudimentary at first. Like, oh, print out this variable name. But when you learn those basic tools, kind of like when you learn basic notes, like what? There are 8 notes. A, B, C, D, E, F, G, A, B, C, D, E, F, G. 7 notes? There's no H, I don't think. 7 notes. I'm not a musician. I wish I was. I like playing music. But when you learn those notes, then you can make all kinds of music. And so kind of like when you learn the fundamentals, you can create all kinds of programs. It takes a little bit of time. It's a craft that requires devotion. Just like music is a craft that requires devotion. Describe how programmers construct a problem statement from a description of a task. So, a description of a task, like maybe the task is that Bob enters, this form, and I'm not, you kind of, how do you construct a problem statement? I'm not sure what a problem statement is. I didn't read this chapter. Problem statement programming. Let's see. Problem statement is an integral part of creating any question, at least one sample. What is an example of a problem statement? Problem statement is a clear, concise description of the issue that needs to be addressed by a problem-solving team. Okay, so problem statement is just going to be like, here is what is not working well, and here's a statement of how it's not working well. And so description of a task might be Bob is manually entering information on a paper form, and then he has to file that form. And the problem statement might be, what is an example? For example, our problem is that we don't have an ERP system method. The process will get followed to solve the problem. Yeah, so the problem might be, Bob is using an antiquated way of keeping track of customer information. We're going to implement a CRM, customer relationship management system, and connect it with a database, so all that stuff is not stored in a filing cabinet but in a database, and then it'll all be searchable. That's kind of a stupid thing right there. Explain how programmers use flow control and design methodologies when developing programs. So computers read software in 3 main ways, and this is called control flow, right? And so they read basically from top to bottom. So you write code, and they read that from top to bottom. And there are 2 places where that top to bottom flow, right, will change. And if you hit iterations, it'll start to loop, right? So that's a loop. So that's one flow control structure. So one flow control structure is sequence, and that's top to bottom. And then iterations or loops is another control flow structure. And if-then tree branch decisions is another one. So if this, then do that. If that, then do this other thing, right? So those are the 3 control flows. And design methodologies when developing programs. So different design methodologies. People have ideas about how software should be built, like object-oriented programming or structured programming or, data design, right? Like there's different ways you could design software. And so those are different methodologies for designing software. Discuss the categories of programming languages and the roles of the compiler in the integrated development environment and coding. So categories of programming languages. When you talk about languages, there's different generations of language. There's machine language, that's the lowest, right? And then on top of that, there's assembly language. And then on top of that, there are 3rd generation languages, which are procedural languages. Wait, 3rd generation languages are procedural. I can't remember where procedural comes in. But third generation languages are the programming languages we operate in. And then fourth generation languages are like SQL, which are starting to approximate natural language. And then fifth generation is natural language. So third gen is pretty much where most of the programming languages reside. And SQL is considered, structured query language is considered fourth gen. It's getting closer to human language, I guess. Though to me it's no easier, harder to use than any third gen language. So those are some categories of programming languages. And then different languages are good for different things. So like there's a programming language called Go, which we're learning in this class, which is really good for what Google does. YouTube is built in Go, and a lot of Google is built in Go. And so it's really good for networked distributed environments. That's Go. And then, you know, there might be different languages that are good for building desktop software, or there are languages that are good for building desktop software, or languages that are really good for video games, right? Because they're fast. And so there's different categories of languages. Different languages are built for different things. The role of the compiler. So when you write a program, you're writing it in code, and then a compiler is going to take all that code you wrote and take it from that third gen language down to machine language. So it's going to translate it from the language you wrote it in, the third gen language, and it's going to compile it, which I think of it as turning it into a big pile of zeros and ones. Compiles it down to zeros and ones, which is machine language, which is what the computer is going to read. So that's the compiler. And an IDE, an integrated development environment, is software that you use to create software. So like one example of an IDE is VS Code. And here's Visual Studio Code. So this is like the best one right now. And then you could see images here. And this is, you know, where you write software. So you have like, you know, the program, your different files. And you open the file and you're working on your code over there. But that's what an IDE is. You can close all those tabs to the right. And then identify the role of debugging in program development. So debugging, originally computers... Let me show you this Grace Hopper bug. So originally computers were these big things. They took up rooms. They had vacuum tubes. They ran hot, and then a moth flew into the computer and died and shorted the computer out. So this woman, Grace Hopper, I'm just looking to see her name, Admiral Dr. Grace Murray Hopper. She had to go in and debug the computer. She literally had to take the bugs out of the computer. And so that's the first actual bug she found. So we still say when you fix a computer or program, you're taking the bugs out of it. You're debugging it. And so today we aren't literally getting bugs out, but if we wrote software that had a mistake or an error in it, then that would be a bug, and we debug it by finding that error and fixing it. And there's two types of bugs. One type of bug won't let your software run at all, and that's like, and then another type of bug is a runtime error. Logic error. There's logic errors and syntax errors. Logic error versus syntax error. So logic error is, I haven't thought about this stuff since last spring. Logic error is like when I say 2 + 2 and it gives me the answer 7. Like the program ran, but it didn't use the right logic, right? So it's a logic error. It didn't do math correctly. A syntax error is when I didn't type in the programming language correctly, and so it won't even run at all, right? And so that's a syntax error. So then I have to go find that error. So that when debugging is finding those errors and fixing them. Explain the importance of testing and documentation in program development. So testing allows you to test your code and make sure it's running. And you could write automated tests, which test. So you could say, here's my chunk of code, and you could write a test to test that code. And you could say, when this runs, it should produce the answer for the example where the inputs are both 2 and 2, right? And then if that test ever doesn't get 4 when it runs, then we'll know there's some error and we could go fix it. So that's testing. And documentation is just leaving like notes about, here is what this program does, here's why I wrote it this way. And so if anybody comes along to work on it other than you, they kind of have some idea about it. Discuss driving factors behind the popularity of various programming languages. It just depends upon what the language is used for and how good the language is. Go, to me, is the best language that exists today. Summarize the considerations. So if you're going to learn a language, you're learning the right one that we're learning in this class. Summarize the considerations in identifying an appropriate programming language for a specific setting. Well, what's the purpose? So do you need a distributed network application? Use Go. Do you need something that's lightning fast and runs on desktop computers? Maybe C++, right? Compare and contrast modern programming languages. Wow, that's just huge. We've kind of done that a little bit. State key principles in the development of future programming languages. Key principles in the development of future programming languages. When they created Go, they wanted it to be, they wanted it to run fast, they wanted it to compile fast, and then they wanted it to be easy to use. And so those were kind of like things that they were going for when they created Go. So I don't know what the author of this textbook came up with for what the key principles are. So I think that's a pretty good, I think we did a good job sort of talking about all that. And there's 31 slides here. So we're going to just rifle through these really quick and see if anything jumps out that we need to go over. Understanding programming helps with complex stuff. And a lot of stuff is just, needs to be automated because it's boring and repetitive. And a career in programming offers great jobs, great salaries, and telecommuting. It's fun, and you get to do interesting things. And, you just hang in there and keep doing it, and you get good at it. But you sit a lot at a desk, which kind of sucks. And, yeah, that's the suck part. So I like academia because I'm walking around campus, I'm standing in front of a classroom, I'm walking, I like that about it. But after you've done programming for like 10 years or 15 years, you move more into the management side. Programming is necessary when there's no existing software for the task. So there we go. What's next here? Information system collection pieces. So this is systems development life cycle. And information system includes, information system is a system that has information in it, and that information is made up, that system's made up of data, people, procedures, hardware, and software. And here's the problem-solving steps in the systems development life cycle. And then here's the PDLC, the programming development lifecycle, another problem-solving steps. You can kind of look at those steps. They're very similar. It's just problem-solving process. And problem statements, clear description of tasks to be performed, understand goals of programming, and interact with users, data, information, methods, whatever. PDLC, error handling, testing plan. Algorithm is a set of steps to describe what a program must do to complete its task. So an algorithm for making toast would be get the bread, open the bread, pull out 2 pieces of bread, put the bread in the toaster, push down on the little lever, wait until the toast pops up, put olive oil on the toast or whatever you put on your toast, right? And that would be the algorithm for making toast, right? It's just a set of steps to describe what a program must do to complete its tasks. Algorithms represented through flowcharts. Flowchart is like, kind of diagrams, the control flow stuff, the sequence, the loops, the conditional logic if statements. Pseudocode is a text-based approach to documenting an algorithm. So you just write out the code in human language text, not programming language. So here are flowchart symbols and what the different symbols represent. And then here's an example of a flowchart and flow control. This is a conditional. It's an if statement. And I don't see any loops there. What was a loop? Rectangle, parallel, input, output, process, terminate, direction of flow. Top-down design approach in which a problem is broken down in a series of high-level tasks. So, different methodologies. Top-down design is taking a big problem and breaking it down into smaller problems. Object-oriented analysis. Programmers identify model classes, solve problems. So this is OOP, object-oriented programming. And it relies upon reusability, inheritance, and classes. So I just code like one time what a car is, and then I replicate that code in my video game every time I need a car, and I could change variables about each of those replicated instances of a car, like what's the color and how fast does it go and that kind of thing. So that's OOP. And coding, translating an algorithm into CPU instructions. Programmers move from algorithm to code by identifying key pieces of information, flow of each step, converting the algorithm into specific programming language. 5 generations of languages. Portability, variables, comments, compilation, compiler, some languages. There's an IDE. Whoa, that's a really bad IDE. Debugging, runtime errors, logical errors. Internal, external documentation. Yeah, so JavaScript is really popular. Rio Waller teaches a great JavaScript class at City College. I'm just looking through the rest of these. Yeah, C++, Visual Basic, don't ever learn it. Java, don't learn it. C#, don't learn it. Objective and C and Swift. JavaScript for sure. HTML for sure. XML, JSON, Ajax, yes, if you do. Yeah, that's good to know. So programming. You know, there's a really good thing to know about, and it's called Stack Overflow Programming Language Survey. Developer Survey, here it is. And so you can learn about the different languages and, you know, like what are the different technologies, most popular technologies, right? JavaScript kills it. And just because it's most popular, don't like say that's the one I need to learn, because like, yes, learn those 3 and okay, maybe, but stay away from it. And yes, learn it, and okay, maybe, no, don't learn it. And yes, learn it. Learn Go, right? So JavaScript, HTML, CSS, SQL, and you know, C and Go, you're good to go, right? You'd be good to go. And you could see like top paying technologies like Go is $74,000 a year, and you know, that's one of the highest paid. That's great. What else can I say about that? I had one student who went from $50,000 a year salary, $25 an hour, took 2 of my Go classes, and then he got $150,000 a year salary. So that went up to $75 an hour from $25 an hour. And if you want to learn how to code, go to Udemy, Todd McLeod. And so this is great, right? Quarantine, you're staying at home. And start out with this class, Visual Studio Code Tutorial, right here. Start out with that class. And then after that class, come up here and take this class right here. Learn how to code. And then after that one, take, you know, like, maybe you could do web development, or you could go after Visual Studio straight to HTML and CSS. So you could do either way. This one first, and then you could go to HTML and CSS to build websites, or you could go up this to, you know, learn back-end programming. This is a more traditional programming, so that would be a good one to jump in on. It's a great class, so really worth checking out. And then if you want to learn about databases, I thought that was up here. It's on the next page. Yeah, here's databases. Sweet, 4.6. That's rising. I'm liking that. That's a good one. So that's a good place to go if you want to learn to code. Man, you make money. You make good money if you're a coder. All right, that's week 10. Hang in there. You're doing great. You are doing great. You're doing the right thing. You just keep going to school. Just keep showing up. Keep doing the work, and you get places. Okay, that's the way it works. Just have grit. Just hang in there. And in your free time, go to Audible and get books and listen to those when you're working out, when you're doing stuff, and that helps you do better in life. And so look for things that you should listen to, like Grit, Angela Duckworth, or Smarter, Faster, Better, right? And that's all going to help you get more on point in your life, and you'll learn stuff when you're working around the house. So see you next time.